where she said, okay, I'm going to change this fraction and this operation. You're not changing the fraction. You're changing the operation from division to multiplication by the reciprocal of your second fraction here. So the x squared minus 9 becomes your numerator, and the 36x to the negative 2 is your denominator now. First fraction remains exactly as it is. Now, the problem here is some students think, oh, I'll just start multiplying now. But if you multiply this times x squared minus 9, you're getting this 9th degree, and you're getting big numbers. And down here, yuck, you know, it's going to be nasty. And then you have to say, how do I reduce that? I can't factor that. I've made it much more complicated, right? So before you actually multiply, you want to check out and see, can I factor anything? Can I factor? Because you want to factor and reduce before multiplying. Factor and reduce. And remember, the idea of reducing is finding common factors to the numerator and denominator, right? Factors to both numerator and denominator. Num and den, that's what I do. Num and den, numerator and denominator, okay? So 24x to the 5th is already factored. The only thing you could do there is change 24 to prime numbers like 2 times 2 times 2 times 3. We don't really need to do that because we're comfortable reducing numbers, fractions out of numbers, okay? So we usually don't tend to do that. But things like this, x squared plus 7x plus 12, it's a lot nicer to see that factored out. So let's take a look at that. So how do you factor something like this if you're left on your own? How do you do that? Clay, do you have a method for that?
Yeah, I start by just finding
factors of 12, yeah. So you do a little list, or you just do it all in your head?
I do, well, I do it all in my head.
Yep.
Find one that have the potential
Yep.
to add up to that's the second.
Okay, so factors of 12 that add up to 7. Okay, so if your head isn't that good at holding all these possibilities, off on the side of your sheet, you could just do something like this. So those are the factors of 16, right? And you could just see, 12, and then you could just see which one of these combination of factors would give you, if you added them, 7 in the middle. And it's this combination. These would be used if you had something like a 13x in here, you'd use 12 and 1, and 8x, you could use 6 and 2. Yeah? Yep. Yep. Oh, cool. So you kind of start with the middle number, 7, and think of 4 and 3, 6 and 1, like that? Yeah. Oh, that's cool. Yeah. That's actually kind of reduces the number of possibilities sometimes, right? Depending on how big this number is here. Yeah. Okay, that's cool. Okay. So what about once you find the numbers, then you put them in, and what do you know about the signs here? All positive, right? Because you've got a positive 12, which tells you they can either be both positive or both negative. And since your middle term here is positive, they're both going to be addition signs, okay? So, and then your other numerator is the difference of 2 squares, so you factor that. And then you have your 36, x to the negative 2. Now, this is a nice thing about a fraction where everything is factored. You can separate this in any way you want. You could now pull this out to just divide the two numbers all by themselves, just like that. You can pull it out so you have your 2 powers separated, just like that. Okay, and then look, you can do it with any combination you want. You could put your fufu, pull your fufu out like that. There's your factor of 1, and then you have x minus 3 over x plus 4. It doesn't matter, and it really doesn't matter where they are in the top or bottom, because there's your fancy form of 1 right there. That's how you can reduce this at this point. You can also find a factor that's common to both 24 and 36. You may not find the biggest factor right away, which is 12, right? But you could maybe do this in steps. And that's what a lot of people do. They pick a number that they recognize first, maybe like 6 into both of them, and then they keep reducing it and reducing it. Yeah. So we know 2 and 3 are both prime, so we're done with that. We can see that we have an x minus 3 in the numerator, and there's no other x minus 3s in the denominator. We have an x plus 4 in the denominator. There's no other common factor in the numerator. And now it's just a question of remembering how to deal with that, right? And remember the little acronym I gave you. When you divide, you subtract exponents, right? It's part of Mad Sex, right? You divide, you subtract the exponents. So you have x to the 5 take away -2, which is 5x to the 5 plus 2, which is x to the 7th. So x to the 7th goes in the numerator. Or as Amber mentioned, if you don't use that, you can also use the idea that you can change the position of any power by moving it from the numerator to denominator or denominator to numerator if you change the sign of the power. I have every right in the world, if I wanted to bring this x to the 5th down to the denominator, but then I have to call it x to the -5. Okay, so one of Sandy Goki's 095 students talked about happy and sad babies, and we would call this a sad baby because the baby's been put down, so it's crying. It wants to be picked up, and then it's happy. I love that little story that student made up. I thought it was perfect. So when you bring the x to the -2, if you want to put it in the numerator, notice when Amber put it up there, it became happy. It became a +2 once its position was changed from being put down to picked up. So there's all kinds of ways to remember this and do for you whatever works. Some of you are very comfortable just applying rules and you remember them easily. Other people can't remember rules. They get them all mixed up. So they have to have some other way of remembering them. You're all different. Okay, so do whatever works for you. Any questions on this before we move on to today's material? All right, so for today, if we looked at your homework here for today, let's go to your homework. Part of your homework was to do preparation for class 2. And what does doing preparation for class 2 look like? To do that, you go down to the bottom of the page, and here's your preparation for class 2. Before you walked in here today, you were supposed to quickly read section P1 and be prepared to discuss the preview exercises at the beginning of today's class notes. And those preview exercises look just like this. So, want to read me this first one, number 1 here? James, want to read that for us? Right now, you're going to use math. You're going to take a look at problem number 2 at your seats. I would encourage you, since we have a small class, to share among you. If you want to answer these bullets and then go walk from one table to the next to see if you're in agreement, great. I will give you maybe 7-8 minutes to do the bullets for number 2. So we're going to start the teaching demo no later than 11:10. We'll start the teaching demo. So work on number 2 at your seats with your table mates. So let's just take a few observations from the peanut gallery, okay? You're the peanut gallery. So let's just take, where does peanut gallery come from? Does anybody know that phrase? Do you like to look up like where like different phrases and ideas like that come from now?
Doesn't it come from like back in the old days when we used to do cake?
It's in the front, yeah. And did they throw peanuts at the people in the play, or did it go the other way? I mean, where did it come from? Do you know? Oh, no, I think it does have to do with theaters and where the position of the people. Anyway, if you're curious, look it up. I love that kind of stuff, like knowing where things come from. I could look it up too, but it's kind of when, I don't know, I'm going to be busy watching the Super Bowl on Sunday. I don't know. Anyway, so observation, table 3, right here. Observation, what you guys notice? It steadily increases. I like that idea that you used there, James. It steadily increases. Steadily, I think I wrote that. And what does he mean by it? What does he mean by it? Tuition and fees, right? So tuition and fees steadily increases. Okay. Okay. So in other words, it doesn't go up and come down and go back up and down, right? It's steadily increasing. Steadily usually implies what type of idea that you've probably talked about in mathematics along the way? What kind of graph has a steady, what you call a steady increase? A line, right. And we call that steady, a constant thing for a line, the slope. But as, is it Marissa? Melanie, I had the right first letter. What Melanie noticed was even though it's steadily increasing, it's not increasing by a constant amount from year to year, right? So the steadily is true because it is increasing every year, but it's not constant. So we couldn't say y equals mx plus b exactly, right? We couldn't find an m and a b so that you put in the year and out pops the number you have here. But maybe a straight line would be a pretty good estimator of this because it's steadily increasing. What else do you notice? Tuition doubles from when to when? Yeah, so it almost doubles over the decade, right? So tuition and fees like practically double, right? Over the decade, which is that 10-year period. What else do you notice? Anything else? Vivian? Yeah, look at what happens between 2003 and 4. It's the largest increase, isn't it? It's the biggest jump in tuition and fees. So between the years 2003 to 2004, we have the largest jump, or the biggest jump, however you want to say it, or increase, I guess is what Fabian said, increase in tuition and fees. Okay, good. So what's this little thing there mean, that little squiggly line? Does anybody know? Some numbers that aren't shown. What numbers? From 0 to 2,999, right? So basically they said, geez, these fees are starting in the 3,000 range. Why bother putting in the vertical axes from 0 up to 3,000? So they just snipped it out. But when you do that, you have to indicate it, okay, with a little break in the axis. So that leads to the question, why didn't they put one here? You can put one on either axis. It doesn't matter. Why didn't they do it here? You'll see in a minute why. At least why I think they didn't do it. Okay. And then what questions are you interested as a student that you, maybe you could get answered? Yeah, Clay?
As to why it jumped so much, because this is 2010. So it said it's going to adjust it for inflation.
Mm-hmm.
So logically, if that graph has to be like an exponential graph, meaning that it gets closer to normal. So why is it that suddenly it's gone some more vertical in growth in these 10 years?
Because it's been my understanding of inflation is that if it's, you know, these are actual real costs over and above what would, in other words, you just don't take the dollars from 2000 and put them into 2010 dollars, what's equivalent. These are the actual increases. That's my understanding of how it works.
Right. So, but it's just why isn't it more steady all the way down? You can see the smallest
Because inflation isn't constant. So it's not like inflation from year to year is the same. Okay, what else might you be interested in as a student? Anything else? About what do you think when are you going to be going to college, for how much longer you think? All right, just give me an idea. Right, well, just give me an idea, like 2017, reasonable? Yeah, some of you might still be in school in 2017. What do you think tuition and fees will be in 2017? That be a logical question you might have? Do you think it's going to be going down? No, not me either. Okay. All right. So one of the things, why don't you read the number 1 here for us? Dean, how about reading number 1 for the teaching demo?
The good news is that it may be possible to answer your questions in mathematics. We work with a real data collected presented in the bar graph, or more simply, a model. Model is a mathematical representation, such as an equation, of a real-world situation. We can describe the relationship of two or more quantities with writing an equation. This is an important step in some problem solving, being able to convert a description of a relationship.
So what kind of relationship are we looking at here in our bar graph between what two quantities? What are we trying to find a relationship? What kind of cost, the cost of tuition and fees over time, right, or with time, right? We want to see, is there any way we can describe or find some kind of equality between those two things? Find a mathematical equation that says this is what tuition will be given this particular time period. So let's do it. Let's use our model. Well, the author gave us this model right here. He said we can estimate or closely describe the tuition and fees, the cost for the tuition and fees with this model. 4x squared plus 341x plus 3194, where x is the number of years after 2000. So if x is representing the number of years after 2000, what would be the x coordinate for this point right there, the year 2000? What would I use for x to describe the year 2000 if it's the number of years after 2000? What number? 0. So that's why I think they didn't put that little squiggly mark there, because they knew that with their modeling they were defining it as the year 0. That's my guess. So what would I use for x if I wanted to estimate the tuition and fees with this model for a year 2001? What would I use for x? 1, right? And so similarly, you can go all the way up and change each of these for the purposes of our model and how we've defined our x value. You can replace those years with the numbers 0 through 10. Okay. Now, if this little thing is not on your lecture, your class notes, your teaching demo, what I did is I took these points, 0, 3,362, and I plotted them in my graphing calculator. So I took each one of these points, and you can see their representations here. And then I asked my calculator to come up with an equation that tried to go through as many of those points or got as close to those points as possible. That's called, that fits the data really well, fits it. Just like clothes, you want your clothes to fit you really well. And this is the equation. It came up with the same equation as your author. Okay, and we're going to talk about this a lot in this class, how to find these equations and what to do. But for right now, I just wanted to show you that it sort of is like doing something like that right near your data. Okay, that's not exactly this curve, but it's close. All right, so here's our model right here. T equals 4x squared plus 341x plus 3194. We know what x is and we know what t is. And if I asked you to use this formula to find the average cost of tuition and fees at U.S. public colleges in 2010, how do you start? How do you start a problem like this? What do you do? By replacing x, and what would you replace x with here, Fabian? 10, right? Because the year 2010 is 10 years after the year 2000. So for our model, x is going to be 10. So everywhere you see x, you replace it with 10. And did you leave your bag in the studio? Oh, okay. So now we have an equation where we filled in the value for x, and now we can compute it, evaluate it, find the value, and we get 400 plus 3,410 plus 3,194. And this is telling us that in the year 2010, our model estimates the tuition and fees to be $7,004. So our model estimates that in the year 2010, our tuition and fees, blah, 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 will be $7,004. So notice something here. When I wrote this sentence out, I'll be asking you to write sentences a lot for your answers. I've used the units. I didn't just write 7004. I gave the units that measured that number, which was dollars. Those were the units. And I converted the 10 to what it means in terms of its context. It was the year 2010. And my sentence describes what this solution means using both of the units that are being discussed in the graph. Okay, and both of the units for the variables here, the variable for tuition that represents tuition and the variable that represents the year after 2000. Okay, so this is the type of sentence that I would be expecting, something like that. Right? What do you think about that estimate if we compare it to the actual value for 2010? What do you think about it? It's pretty darn close, isn't it? It's pretty good. It's pretty good estimation. So let's see, someone from table 5 I haven't heard from today. Sorry, I forgot your name. Right here, you. Kara. So Kara, do you think that this is an overestimate or an underestimate of the actual value for the year 2010? It's totally underestimating it, right? And by how much does it underestimate it? By $16, right? Okay. So what I would like is I would like table 2 and table 3 to find the tuition and fees that are predicted for the year 2014. Notice I used the word predict. Why do you think I'm saying predict here? Does anybody have a sense? Anybody have a sense of why I'm using predict? Yeah, Dean?
This is unnecessarily accurate.
Right, well, it was my estimation, right? Because a model's not necessarily going to give me exactly the same as the data. But so here's the difference, Dean. I was talking about estimating when I was talking about 2010, estimating now I'm talking about predicting for 2014. It hasn't happened yet. It's not part of my data set, right? My data set only goes from 2000 to 2010. So if I'm working within those years, I'm making an estimate, right, of what we can actually see. If I go outside on either end, I'm making a prediction because I can't actually see it in my bar graph. Okay. That's called extrapolation when you go outside of your data set. So both of these questions are extrapolating because this is the future and this is the past, right? So this is called you're extrapolating. That's the fancy word, extrapolation. Okay. When you're within the data set, like up here, within your data set for 2010, that's called interpolation, I-N-T-E-R, like interstates. They go right between, you're between the data set, interpolation. Okay, so I'd like tables 2 and 3 to find the answer for this. Tables 2 and 3, and then check with each other before you come up and put your answer in. And I'd like tables 4 and 5 to discuss this 1990, and make sure you agree before you come up and write the answer up here, okay? So take your time. The answer for 1990, does it seem plausible? No.
But
It says that,
Hang on. Can we just, you're not going to go down to the note now, are you, Fabian? Okay, okay, go ahead. I thought, okay. Yeah, go ahead, sorry.
the number 3 says that it models the average tuition and fees for college years and years after.
Yeah.
2012.
Well, whether you're after or before, your model is still only really pretty accurate for 2000 and 2010, right? And what you're saying is because this is before 2000, this model isn't really representing the data very well because we know it can't be $184, right? Right? Because that's the problem with going too far outside your data set, because this curve, remember, is going to start going up, but it may not be going as if it's a quadratic. That's what, oops, we've got to talk about that. Talked about it in our first class. This is a quadratic equation because it has a 2 there as your highest power, right? Now, when you read that note at the bottom, this thing has jumped even more so. Maybe it's more like after this, it's growing exponentially, all right? And if this continued all the way down to 1990, it's going really down to $184, which is dropping pretty quickly. And we know that that's not a plausible answer, right? So this is why we use the term model breakdown, and why you have to be really careful not to go too far outside your data set with predicting either tuition and fees in the past or the future. All right, and you can see here this little note I gave you about College Board reports of tuition. Now, my daughter is going to Warren Wilson College, and she was going to go last year, and she decided to take a gap year. And the difference in tuition between the 2 years that of going this year versus last year was over $2,000. Just 1 year, $2,000 difference. So along the way, you've heard of the word set. Yeah, it's simply stated, it's just a collection of things, objects, right? Now, sometimes we can list everything in the set. Like I could list all of the New England Patriots that are going to be dressed for the Super Bowl on Sunday. I can list the name of every single person. And when I can do that, we say that when you can list all of the elements or the objects in a set, which we call elements, it's called the roster method. And that makes sense. I have a roster right here with all of your names on it, right? I can list each one of you individually. So if I was going to represent the set of the Three Stooges, right? And I wanted to use the capital letter A to represent them, there's only a couple of things you need to remember. Every single time you talk about a set and you represent a set, you have to start it and end it with this little curly brace, okay? And then you list each element and you put a comma in between each element of the set. In this case, it's the name of the Three Stooges. Now, excuse me, I was just going to say, I know that the original Three Stooges had shrimp, right? All right, so this was, when I was growing up, they actually changed places, but these are three of the Three Stooges. It's not a complete set, right? Because I really should have shrimp in there, right? Shemp. Oh, is that his name? How do you spell it? Do you know? Oh, Shemp, right. Did you know they were brothers? I just read about, I think it was Shemp and Curly, wasn't it? And Mo, they were all brothers? Yeah, and I just read the whole thing, like over intercession, about why one left and the other one came. Anyway, doesn't matter. All right, see, I can get distracted. So, yeah. All right, so I better do an edit on this, right? And people are going to say, who the heck is Shemp? All right, so let B represent the set of 7 dwarfs. The first table to finish and get it correct gets 2 points on their quiz next Wednesday.